Welcome to the Deep Dive. We're back, and today we're diving into the real-world side of solar thermal energy.
That's right. We're digging into Lecture 11 from Professor Pushpito Ghosh's course, Renewable Energy Resources.
Yep, it was delivered at ICT Mumbai, posted on YouTube back in 2021. It's a great series.
15 lectures in total. We touched on Lecture 10 last time, which was all about the principles of concentrating sunlight.
Exactly. And Lecture 11, that's where Professor Ghosh really shows us how that focused power gets used. So if you're curious about the practical stuff, the applications, this is for you.
It bridges that gap nicely, from theory to actual use cases. And remember, this is just part of his broader look at renewables. Solar continues in Lectures 12 and 13.
But think about a really sunny day, all that energy. What can we actually do with it when we concentrate it? That's what we're exploring today, pulling out the key applications from the lecture.
And for the full detail, the original lecture is out there on YouTube. Check the intro notes for the handle.
Okay, let's jump in. First up, something kind of fundamental, community-scale cooking.
Yeah, Professor Ghosh starts with parabolic dishes, you know, those curved reflectors,
Right, they focus the sunlight.
to a single point. And you get serious heat, he mentions, well over 100 degrees Celsius.
Wow, so hot enough to actually cook with. He paints this picture of communities just putting pots and pans right there in the focus.
It's a very direct application. Simple, elegant, really, using that concentrated solar power for a basic need.
You can almost smell the food cooking, powered just by the sun. It seems like a massive deal for places without easy fuel access.
Oh, absolutely. Think about reducing reliance on firewood or fossil fuels.
Yeah.
It's sustainable, it's local, a very impactful starting point.
Okay, so from cooking pots to something much bigger scale, industrial process heat, making steam, basically.
Now we're talking higher temperatures. Good quality steam, like 173 degrees C at 8 bar, Professor Ghosh mentions. That's useful steam for industry.
And he gives a really cool example, right, from Egypt.
Yes, a pharmaceutical company. Apparently, they use parabolic troughs for almost all their process steam. That's not trivial. It's a serious industrial setup.
That really shows the potential scale. But what blew my mind was the history he mentioned.
Oh, the 1913 system.
Yeah, also in Egypt, using parabolic troughs way back then for pumping water. This idea isn't new.
Not at all. It shows the fundamental concept is sound, you know. We've just gotten much better at materials and efficiency since then.
So how do these troughs work? He explained it. Water in a pipe.
Exactly. A pipe runs right along the focal line of that long, curved mirror. Sunlight hits the mirror, bounces onto the pipe, heats the water inside.
Simple enough. And you can link them.
Yep, connect them in series. The water goes from one trough to the next, getting hotter and hotter until you reach the temperature you need. Very modular.
Makes sense. Okay, let's get specific. He talked about steam distillation, extracting oils.
Right, the limon example. Extracting that citrus oil from orange peels using solar-generated steam.
Limon. That's the orangey smell, right? Used in foods, fragrances.
That's the one. And he connects it to Nagpur in India, known for oranges. It shows how this tech fits into real existing industries and regions. It adds tangible economic value.
It really brings it home, doesn't it? Using solar power for something so familiar. Orange peels to valuable oil. But it can't be that simple, right? How do you optimize these systems?
Good question. No, it's not just set it and forget it. Professor Ghosh talks about optimization. Key factors are things like, well, how much sun you're actually getting the insolation.
Okay, that makes sense.
And also ambient temperature, wind speed. Wind can cool the collectors down, obviously, reducing efficiency.
You need to account for the local weather.
Precisely. And he mentions there are standard equations models engineers use to predict performance, how much steam you'll generate or how much limon oil you might expect. It's based on solid science.
But the sun isn't constant, is it? He stressed that variability, day to day, hour to hour.
That's the big challenge with solar. It fluctuates. So collecting data over long periods is crucial to really understand average output. He noted even the limon yield could vary significantly.
So managing that variability is key. Maybe storage comes in later.
Exactly. Or hybrid systems. You need ways to smooth out those peaks and troughs in supply.
Okay, another angle. Not just steam, but hot air for cooking or heating.
Yeah, another way to use the thermal energy. He gave the example of, say, terraces in sunny places like the Middle East.
Right. Collectors heating air.
And then you just pipe that hot air into kitchens or use it for space heating. It's maybe simpler in some ways than dealing with steam.
Seems practical for certain climates. And he broadened it out. The heating medium could be water for steam, oil for hot oil systems, or air depends on the job.
That flexibility is important. Different applications need different temperatures, different system designs. Using the right fluid, water, oil, air helps optimize for the specific task.
All right, now for the one that sounds kind of weird. Solar refrigeration, using heat to make cold.
Hey, yeah, it seems counterintuitive, doesn't it? But it works on thermodynamic principles. He mentioned an early Indian example, Baroda, 1978.
Wow, that long ago.
Yeah, though he said it wasn't super efficient, maybe 10-15 degrees C cooling, but concentrated solar radiation makes it much more effective.
So how does it actually work? You walk through a cycle using ammonia.
Right, an absorption refrigeration cycle. It starts in the evaporator. Liquid ammonia absorbs heat from the cold space, that's the cooling part, and turns into vapor.
Okay, so heat absorption makes it cold.
Then that ammonia vapor goes to an absorber where it dissolves in water. This keeps the pressure low, pulling more ammonia vapor from the evaporator.
Got it. Then what?
Then a pump sends this ammonia-water mix to the generator, and that's where the solar heat comes in.
Ah, the solar part.
Yeah, the concentrated heat boils the ammonia out of the water, creating high-pressure ammonia vapor. Ideally, he said, you want temps like 150, 200 C here.
But you get some water vapor too.
You do. So next is a rectifier, basically separator to get rid of most of the water vapor, leaving pure ammonia.
Okay, pure ammonia vapor, high pressure.
Then it goes to the condenser. It releases heat to the outside environment and turns back into liquid ammonia.
Still under high pressure, though.
Right. So the final step before repeating is an expansion valve. Pressure drops suddenly, temperature plummets, some ammonia flashes into vapor, making it really cold.
And that cold mix goes back to the evaporator to absorb more heat.
Exactly. The vapor then goes back to the absorber, dissolves in water again, and the cycle continues, driven by the sun's heat in the generator.
That is pretty clever. Solar-powered cold storage. He also mentioned another type, adsorption, with zeolite.
Briefly, yes. Vapor adsorption refrigeration. It uses a solid material, like zeolite, that grabs onto refrigerant molecules, absorbs them at low temperatures.
So the zeolite acts like a sponge.
Sort of. It absorbs ammonia, causing cooling. Then you use solar heat during the day to drive the ammonia off the zeolite. That released ammonia gets condensed. Then at night, as things cool, the liquid ammonia evaporates in the cold box, providing cooling, and the zeolite absorbs the vapor again, ready for the next day's heating cycle.
Interesting. And he mentioned vaccine transport for that.
Yeah, as a potential application where maintaining temperature is critical, maybe off-grid. It's another approach to solar cooling.
Okay, big shift now. Generating actual electricity. Solar thermal power.
Yeah.
This is different from PV panels, right?
Totally different. Photovoltaics, PV, converts sunlight directly to electricity. Solar thermal power uses concentrated sunlight to create heat, usually to make steam.
Which drives a turbine, like in a normal power plant.
Exactly. Same principle as coal or gas plants, just the heat source is the sun, concentrated using troughs or dishes.
And he stressed again, it's got to be direct sunlight.
Yes, only direct radiation can be effectively focused. Diffuse light, like on a cloudy day or in hazy conditions, doesn't work well for concentrator.
So location matters a lot. He mentioned Mumbai, maybe not ideal because of pollution haze.
Right. Cleaner, rural areas with high direct sunlight are generally better suited for these large-scale concentrating solar power plants.
He also talked about not heating water directly, but using thermal oil first.
Yeah, an indirect method. You heat a special oil to maybe 400 Celsius using the focused sunlight. Then you use that hot oil to boil water and make steam separately.
Why do that? Seems like an extra step.
It can reduce risks. You don't have high-pressure steam circulating through all the solar collectors, potentially lowering corrosion and leak issues. The oil system can operate at lower pressure.
Okay, safety and materials considerations.
Now,
efficiency. You really hammered on temperature for power generation.
Absolutely critical. Basic thermodynamics. The hotter the steam you feed into the turbine, the more efficient the conversion to electricity. Low temps mean terrible efficiency.
He was talking numbers like needing maybe 1,000 C peak temps to get operating steam around 300, 350 C for like 18% efficiency.
Something like that. You need those high operating temperatures, 400 C, 500 C or more, to get decent thermodynamic efficiency out of the Rankine cycle that power plants use.
And getting those temps relies heavily on the receiver surface, the part that absorbs the light. He talked about solar selective coatings.
Yes, these are crucial. You want a surface that absorbs almost all the incoming sunlight high absorbance, alpha.
Soaks up the heat.
But you don't want it radiating that heat back at low emittance, epsilon, especially at high operating temperature.
So high alpha, low epsilon, traps the heat effectively.
Exactly. Maximize that ratio. And the coating has to survive extreme heat without breaking down. He mentioned work at NAL in India, but maybe more for lower temps.
Yeah. Sounded like high-temp coatings might still be imported. Seems like a key R&D area.
Definitely. Better, cheaper, more durable coatings directly impact plant efficiency and cost.
Okay, but the sun sets. How do you get power at night? Energy storage, right. Molten salts.
That's the leading solution for large-scale thermal storage. Mixtures of salts, like sodium and potassium nitrate.
And they stay liquid at really high temps.
Yeah, up to maybe 600, 800 degrees C. They have good properties. They flow reasonably well, don't boil off easily, and crucially, store a lot of high heat capacity.
So you heat up this huge tank of salt during the day.
Using maybe a field of heliostats focusing on a central tower receiver.
And then at night, you pump the hot salt through a heat exchanger to make steam for the turbines.
That's the concept. It allows the plant to generate power much more consistently, even when the sun isn't shining. Molten salt storage is a really active research area.
Very cool. Okay, going even further, he talked about using solar heat not just for storage, but to drive chemical reactions, solar chemical reactors.
Yeah, moving beyond just heat storage to creating chemical fuels using that high-temperature solar energy. Think, maybe 1,000 degrees C or more.
What's the advantage there?
You're storing the energy in chemical bonds. Chemical fuels are generally easier to transport and store long-term than heat, and you could potentially use them in fuel cells or other processes later. Some cycles even recycle reactants.
And the ultimate goal here, the holy grail, as he put it, water splitting, making hydrogen.
Directly using solar heat to break water, H2O, into hydrogen, H2 and oxygen, O2. That's the dream for clean hydrogen fuel.
But he said just heating water doesn't work well. You need insane temperatures.
Extremely high, like thousands of degrees C just to get a small percentage to split thermally. The activation energy is just too high.
So you need clever chemistry. He went through several cycles, starting with sulfur iodine, the SI cycle.
Right. It's a multi-step thermochemical cycle. It uses iodine and sulfur compounds as intermediates to split water at a lower maximum temperature, around 850 C.
How does that work, basically?
You have a low-temperature reaction making hydrogen iodide, Hi, and sulfuric acid, H2SO4. Then you use high solar heat to break down the H2SO4 into SO2, water, and oxygen. And another high-temp step breaks down the Hi into hydrogen and iodine.
And the sulfur and iodine get reused.
Exactly. They're recycled in the process. The net result is just water in, hydrogen and oxygen out. It's complex, uses corrosive stuff, needs good separation.
But it works at lower temps than direct splitting.
Considered one of the most developed cycles, yeah. All fluids, potentially high efficiency.
Okay, then cerium oxide.
A two-step cycle. High temp step, like 2000 C, where cerium oxide releases oxygen. Then a lower temp step, maybe 400 C, where the reduced oxide reacts with water to make hydrogen and regenerates the original oxide.
Conceptually neat, but 2000 C, yikes.
That's the big hurdle, very challenging material science problem.
Copper chlorine cycle, lower temp again.
Yeah, around 500 C for oxygen release. Multi-step involves copper chlorides, also an electrolysis step.
Wait, electrolysis? He questioned that, right?
Yeah.
You need electrolysis anyway.
Yeah, why not just do direct water electrolysis? It raises questions about the overall energy balance and complexity versus just optimizing electrolysis itself.
Fair point. And the last one you mentioned, ferrite alumina, isothermal.
Right, the Hersenite cycle. Two steps, but both happen at the same high temperature, around 1400 C. First step releases oxygen, second reacts with water to make hydrogen.
Advantage. No big temperature swings.
Exactly. Less thermal stress. But disadvantage, you need pressure swings, and separating the oxygen cleanly is tough. Still, he called it an important scheme.
Wow, lots of chemical pathways. He also briefly mentioned ammonia and methane cycles for storage.
Yeah, using solar heat for the energy-intensive step, like splitting ammonia into nitrogen and hydrogen, stores energy. Then you can recombine them later to release heat, exothermic Haber-Bosch.
Or reforming methane with steam using solar heat, then reversing it later.
Same idea. Using reversible chemical reactions driven by solar thermal energy as a way to store and release that energy on demand. Worth looking into the thermodynamics, he suggested.
Okay, so lots of future potential there. But what's the reality now for hydrogen? He said it's mostly natural gas.
Still overwhelmingly steam reforming of natural gas. It's cheapest currently, but uses fossil fuel and makes CO2.
Not ideal for clean energy, though maybe biogas could be used.
Potentially, yes. Using biogas from renewable biomass and steam reformers could be a route to greener hydrogen, assuming the carbon cycle balances out.
But the main competitor for clean H2 is electrolysis,
Yeah.
right? Using electricity to split water. He detailed alkaline electrolysis first.
Yeah, the established method uses an alkaline solution, like KOH. Electricity drives reactions at the electrodes, producing H2 and O2. High-temp versions can be more efficient and produce pressurized gas.
Cost has been an issue compared to reforming, though.
Historically, yes, but he stressed that falling renewable electricity costs, especially solar PV.
Which provides DC power directly.
Exactly. That changes the economics considerably. Cheaper, clean electricity makes electrolysis much more competitive, especially if you avoid AC-DC conversion losses.
Makes sense. He also mentioned PEM electrolysis, proton exchange membrane.
Right, newer tech uses a solid polymer membrane that conducts protons, can use pure water, potentially higher current densities, but often needs pricier catalysts, needs careful voltage control to be efficient.
And finally, solid oxide electrolysis, high-temperature steam.
Very high temps, 800, 1000 C, electrolyzing steam, can be potentially very efficient because heat provides some of the energy needed, but scaling it up and material stability are big challenges.
So multiple electrolysis routes are developing. It's not just one technology.
Definitely an evolving field, competing with those thermochemical cycles and trying to displace steam reforming.
Wow. Okay, that really covered a huge range, from cooking food with a simple dish to complex chemical cycles for hydrogen, all powered by concentrated sunlight. Professor Ghosh's Lecture 11 really laid out the potential, some definite aha moments there.
It's impressive, isn't it? The sheer breadth of applications that stem from the basic principle of concentrating solar energy. And you see the connections, material science, thermal storage, efficiency, they're key across the board. It really highlights the ongoing R&D needed for a sustainable energy future.
And the need to think about, efficiency, cost, scalability for each one.
Absolutely. They all have pros and cons, specific niches, perhaps.
So a final thought for you listening. Which of these applications seems most promising for the near future? Or what's the biggest hurdle, you think, to replacing fossil fuels with these solar thermal options? Lots to chew on there from Professor Ghosh's lecture.
Indeed. The challenges are real, but the potential is enormous. Continued innovation is key.
Well, thanks for diving deep with us today into solar thermal applications. Hope it shed some light. Definitely check out the original lecture if you want more detail.
And perhaps next time we'll get into photovoltaics, as Professor Ghosh does in the following lectures.
Sounds good. Until our next deep dive.